Hello again, my physics students. This is Mrs. Buchanan. This is our final video in our study of Newton's first law of motion. Let's review again our big idea that forces cause changes in motion. We will be covering our sixth learning objective, explain how the law of inertia applies to objects in motion. We're going to revisit our man Copernicus, the moving Earth again. Copernicus announced the idea of a moving Earth in the 16th century. This controversial idea stimulated much argument and debate. One of the arguments against a moving Earth was as follows. Consider a bird sitting at rest in the top of a tall tree. On the ground below is a fat, juicy worm. The bird sees the worm, drops down vertically, and catches it. It was argued that this would not be possible if the Earth moved, as Copernicus had suggested. If Copernicus were correct, Earth would have to travel at a speed of 107,000 kilometers per hour to circle the Sun in 1 year. Now let's convert this speed to kilometers per second. Did you get 30 kilometers per second? If so, that's the correct answer. Even if the bird could descend from its branch in 1 second, the worm would have been swept away by the moving Earth for a distance of 30 kilometers. For the bird to catch the worm under this circumstance would be an impossible task. The fact that birds do catch worms from high tree branches seemed to be clear evidence that the Earth must be at rest. So objects move with Earth. Can you refute this argument? Well, you can if you invoke the idea of inertia. You see, not only is Earth moving at 30 kilometers per second, but so are the tree, the branch of the tree, the bird that sits on it, the worm below, and even the air in between. All are moving at 30 kilometers per second. The law of inertia states that objects in motion remain in motion if no unbalanced forces act on them. So, objects on Earth move with Earth as Earth moves around the Sun. When the bird drops from the branch, its initial sideways motion of 30 kilometers per second remains unchanged. It catches the worm and is quite unaffected by the motion of its total environment. So stand next to a wall. Jump up so your feet no longer touch the floor. Are you standing next to a wall? Jump up. Now, does the 30 kilometer per second wall slam into you? Why not? Because you're traveling at 30 kilometers per second before, during, and after your jump. The 30 kilometers per second is the speed of Earth relative to the Sun, not the speed of the wall relative to you. So objects move with vehicles. 400 years ago, people had difficulty with ideas like these, not only because they failed to acknowledge the concept of inertia, but also because they were not accustomed to moving in high-speed vehicles. Slow, bumpy rides in horse-drawn carriages do not lend themselves to experiments that reveal inertia. Today, we flip a coin in a high-speed car, bus, or plane. So that if you do this, make sure you ask your parents in the car before you try this. So you flip a coin in a high-speed car. You catch the vertically moving coin as if the vehicle were at rest. So we see evidence for the law of inertia when the horizontal motion of the coin before, during, and after the catch is the same. The coin keeps up with us. The vertical motion of gravity affects only the vertical motion of the coin. So let's do a quick summary of what we've been talking about from Aristotle to Galileo and to Newton, and in talking about Newton's first law. Our notions of motion today are very different from those of our distant ancestors. Aristotle did not recognize the idea of inertia because he did not see that all moving things follow the same rules. He imagined different rules for motion in the heavens and motion on earth. He saw horizontal motion as unnatural, requiring a sustained force. Galileo and Newton, on the other hand, saw that all moving things follow the same rules. To them, moving things required no force to keep moving if friction was not present. You know, we can only wonder how differently science might have progressed if Aristotle had recognized the unity of all kinds of motion and friction's effect on motion. This ends this lesson. Thank you.